Hey math enthusiast, I'm here to go over some notes on proportionality theorems. The first theorem we come across is a picture that should look familiar because we dealt with something like this in the previous section. So as soon as I see that these two sides in my triangles are parallel, then I know that the triangles are similar. So I can set up some proportion. But in this section it's a little different because the sides that I'm going to be comparing are going to be QT to SU. That ratio is going to be equal to TR over UR. So as soon as I see that these two sides are parallel, I can set up this ratio, and I know it's going to be true. Now, down below, we have the converse, which is saying, okay, if you have this ratio, QT over SU equal to TR over UR, if this ratio is true, and those two are equal, then I know right away that these two are going to be parallel. So in this one example, this picture with a vanishing point, I can see we have this side up top, this side down below, and then it's split by these segments right here. What I'm just trying to demonstrate here is that inside of this picture, I can make up those ratios that we just talked about in the notes. So I could compare 3 to 2, and I can see that that ratio is going to be equal to 6 to 4. Now, if you wanted to, you could set up the ratio differently. I could do 3 to 6, and I could see that that ratio is going to be equal to 2 to 4. So we do have several different options here. So let's see if I can apply a couple of them to this example where I'm looking for KL. So let's start off and call KL X. So one option, I could take these two side lengths and set up a ratio involving them, 18 over 24, and set it equal to these two, X over 44. My other option would be, let's compare these two, 18 over X, and set it equal to these two, 24 over 44. Now, if you notice when I cross multiply, I'm still going to do X times 24. And I'm still going to do 18 times 44. Now, if you want to make it a little bit easier, you're always welcome to try to reduce these two ratios in which you have both the terms. It looks like that 18 over 24, looks like we can turn that into 3 over 4. And then for 24 over 44, it looks like we can turn that into 6 over 11. Now when I go through and cross multiply, we just won't be dealing with as big of numbers. So it looks like I end up with 4x equals 132. And for the other one, it looks like I end up with 6x equals 198. And it looks like in both cases, x is going to equal 33. Now I can always just double check my work. 18 over 24, so that ratio should be equal now to 33 over 44. And it looks like if I divide both of them, I'm going to get 3 over 4. Alright, so just to show you real quick, that's another shortcut you can use. So down here, when I had 3 over 4 equals x over 44, I can see that to get to this second ratio, I multiplied that by 11. So to get to the other part of this ratio, I can take that 3, multiply it by 11, and I'll get x equals 33. So that's another shortcut I can use for these proportions. Next problem, once again, I'm looking to solve for x. So we have x here, which it looks like corresponds with 9, and we have x plus 6 here, which should correspond with this side. Now, the first thing I want to point out is they don't actually tell me that these two sides are parallel. The only thing they give me is that this angle and this angle, they're congruent. Well, these two angles here, this one up top and this one down here, they're actually corresponding angles. All right, and because they're congruent, they're going to make these two lines parallel. All right, so even though it wasn't marked, I can now mark it in my picture. So let's clean this up a little bit. So I've highlighted the parts that I know go together. So I know 9 is going to go with x. And then on the other side, I know my denominator is going to be x plus 6, because these two sides are going to be across one another since they're on the same side of the triangle. But as for this side right here, well, the whole thing is 30, and this top piece is 9, which tells me that this lower piece is going to be 21. Now, in this case, I have x on both sides of my proportion, so I can't really reduce anything. So I'm just going to need to go through, cross multiply, and solve. So I end up with 21x equals 9, and then in parentheses we got x plus 6. So I'm going to end up with 21x equals 9x plus 54. Then it looks like I end up with 12x equals 54, which is actually going to give me a decimal. It looks like x is going to equal 4.5. So it looks like if I go back to my picture now, try to erase some of this, that shorter side is going to be 4.5, and then here I'm going to have 10.5. Now, as I said, you could always set up your proportion again just to check to make sure you're correct. So we could say 9 over 4.5 equals 21 over 10.5. Now, it's a little bit harder to reduce these since they have decimals, but what I can do is just plug it into the calculator and see if I'm getting the same value. All right, and it looks like both of them are going to change into 2. So obviously they're equal, so I know my answer is correct. So for my next example, I'm trying to determine whether or not these two segments are parallel. So we're talking about QT and RS. So are these actually parallel? So in this case, I'm not solving for any side lengths. They give me all 4 sides. So I'm going to set up my proportion then. So we have 18 to 36. And this proportion should be equal to 38 over 80. Well, as soon as I go down to reduce these, it looks like I end up with 1 over 2, and on the other side I end up with 19 over 40, which is close to a half, but the problem is it's not a half. All right, because these are not proportionate, I know that they are not parallel. So for the next problem, I'm actually looking for a value for x that's going to make these two lines parallel. All right, so my goal is for these to be parallel. And if they're going to be, I need to set up a proportion. So I'm going to compare these two sides to one another. So we have x minus 5 over 15. And I'm going to set that equal to these two sides. So I'm going to have x minus 4 across from the x minus 5, and then 18 across from the 15. I can't reduce either of these based on the way I set it up, so I'm just going to need to cross multiply and solve. So we have 18 times x minus 5 on the one side, and then I have 15 times x minus 4. So it looks like I'm going to end up with 18x minus 90, and over here I have 15x minus 60. So it looks like when I rearrange this, I'm going to end up with 3x equals 30. So it looks like x is going to be 10. So it looks like my other side lengths here are going to be 6, and up here I'm going to have 5. So if I were to plug these back into my proportion, I'm going to have 6 over 18, which is going to give me 1 over 3, and 5 over 15, which is going to give me 1 over 15. So this does work out. Last thing I want to point out is actually another way we could have set this up. So I could have compared these two side lengths if I wanted. So I could have done 18 to 15, and then across from the 18 I would put the x minus 4, and across from the 15 the x minus 5. This is another way we can set it up, and it's going to make it a little bit easier because since there's no variable on the left hand side, I can actually just reduce this down to 6 over 5. Which might just make it a little bit easier when I go through and cross multiply. But either way, I'm still going to come to the same conclusion, x equals 10. The next theorem from this section is very similar to the last theorem. The only difference is it doesn't form a triangle. So in this case, we have 3 parallel lines instead. All right, and the side lengths I'm comparing is UW to VX, so these two across from one another. And then I'm comparing it to WY to XZ. Right. Now, as I said, that's one way you can set up the proportion. I could also do UW to WY and set that equal to VX to XZ. All right, when I cross multiply up here, I'm still going to be multiplying the same terms. So I have UW times XZ, UW times XZ, and then WY times VX, WY times VX. The final theorem from this section deals with an angle bisector. So we can see this bisector drawn right here. It's ray CD, and obviously it splits this angle right in half. So angle C up top is broken into 2 congruent pieces. Now, what's going to become proportional is I can compare this side to this side. So one way to set it up is I could say that AC to CB is going to be equal to AD to DB. Now, as I've said, that's one way I can set up my proportion. Another option is to do AC over AD. So both those kind of on the top triangle up here. And then it would be equal to the 2 pieces on the bottom triangle. So it would be CB to BD or DB. Right. Much like the last theorem, when I cross multiply it, I'm still going to be multiplying the same terms by one another. All right, AC by DB, AC by DB. So this next example deals with theorem 6.6, which discussed those 3 parallel lines. So in this case, my parallel lines being DC, EB, and FA. And what I want to do is just complete the proportion. So first thing I want to focus on is what sides they started the proportion with. So we have EF, so I'll highlight that, to FG, and we'll highlight that. So we have those 2 pieces in red. And then the proportion continues across from EF, we have BA. So the next part of my proportion, I want something to match up with FG here. Well, that's obviously going to be AG across from it. So the last part of my proportion is going to be AG. Next example, start off the same way. Highlight the 2 in the first ratio. So they're telling me it's a ratio of EG, so it's a little bit longer. So EG matches up to ED. And then my proportion continues. Across from ED is CB. Okay, so I can see that these 2 go together in my proportion. So the last piece I want to go with, if I want to match up with EG, is going to be BG right here. So I'm essentially just trying to match up the parts that I know are going to go together in my proportion. So for the next one, they start off with GF, so it's this short piece up top, which they're saying matches up with FA. So that's kind of the base of the triangle, or one of the parallel sides. And then they jump to GD. So GD is going to be this whole entire thing. So remember, that matches up with this red side right here. Okay, well next they went to the base, so now what I'm going to match that up to is this base down here, because I'm dealing with the whole large triangle. So I know my answer is going to be CD. Now, if you're having trouble visualizing it, another way to look at it is just break it up into triangles. So you have your triangle, small triangle, FAG. Okay, the two parts they matched up were the top piece and the left piece. And then they jumped to the larger triangle, which was GDC. And then this side, FG, was going to match up to this side in my other triangle. So then obviously this left-hand side, FA, was going to match up with DC here. So maybe that'll help you visualize it a little bit better. So if that helps, you can break it up into the 3 separate triangles. Let's take a look at the last example. For the final one, my first proportion is EB, so the one parallel side, which is matching up with FA. And then they jump to saying that FA, so now I'm on the bottom, FA goes with GA. Alright, so once again, think about it like the triangles that I broke it up into earlier. So that means EB, this base right here, is going to correspond with this whole entire side right here, which is going to be BG. For the next example, I'm trying to solve for x. Now, they didn't necessarily tell me that all 3 of these lines are parallel, but because they show me that we have right angles with all 3 of these lines and this single transversal, then I know right away that they have to be parallel. So in that case, I can use the theorems that I've learned. I can apply it here. So now I just need to set up my proportion. So we have 2 options. I can match up x to 36, the side across from it, and then to complete my proportion, we can do 51 to 54. As I said, if you don't like that, what you can do is you can do x to 51 and then set that equal to 36. 36 to 54. It's up to you. Either method's going to work. As I said, if you want to, you can try to reduce these ratios to make it a little bit easier when you cross multiply. Really doesn't matter. Either way, I'm going to end up with the same solution. So it looks like I end up with 54x is going to equal 1,836, and then when I divide by 54, it looks like x equals 34. Next example deals with that angle bisector theorem. So I know when this is bisected, I can set up some sort of a proportion with what it's broken into down here. All right. Now, the pieces I'm going to compare for my proportion are going to be this side right here. So we'll do 24 to this piece that's on the side with the 24, the x. And to complete my proportion, I'm going to set it equal to the 8, the other leg on my triangle, over this piece right here. Now, the thing is, they don't label that side. I know the whole thing is 28, and I know that this piece is x. All right, so for example, let's say x was 10. Well, I would know right away that this side is 18. Well, the problem is I don't know what x is, so instead of labeling that as 18, what I'm going to label it as is just 28 minus x. Because whatever x is, that's how I would find this length. I would just take the whole thing minus x. So that's what I'm going to fill in here down with my proportion, 28 minus x. As soon as I have it set up, now I can just go through, cross multiply, and solve. So I'm going to end up with 8x equals 24 times 28 minus x. So I end up with 8x equals 672 minus 24x. I'm going to end up with 32x equals 672. And lastly, it looks like x is going to equal 21. So I really had 21 up here, which made this side over here 7, that shorter side. And now the last thing to do is just to check to make sure this is correct. My ratio would then be 24 over 21, and then to complete the proportion, it would be 8 over 7, which it looks like is correct because both of them obviously reduce to 8 over 7.